So the next speaker is Michail Sapkas, who studied physics at the University of Crete in Greece, specializing in physics of data, a multidisciplinary program of data analysis and statistics, hardware, neural network, and programming, but with a solid physics core. To combine all this together, he's working on hardware implementing neural networks for physics, and this was his natural progression for his work. In the last year, he worked with the Versal AI engines, and we hope that the work that he's going to present today will engage your curiosity on this new computing paradigm. Please.
Thank you, and good morning, everyone. I'm going to talk, this is the first time I'm going to talk about this, so I'm going to show you how we implemented a recurrent neural network on the AI engines of the Versal. And first, I will have to introduce you to all this stuff. But the motivation to do so why we want to do that. So about a year ago, I worked with a very capable team and very intelligent people. They wanted to design a controller for a synchrotron machine at the Karlsruhe Institute of Technology. And they wanted to replace PIDs with a reinforcement learning framework. So the way you do it is that you observe the status of the beam, then you enter the observations to a model. It spits out a modulation on the RF cavities. And you're trying to control some induced instabilities. So in order to do so, you have to be fast. You have to be faster, or at least at the time scale of the physics you're trying to control. And here we're talking microseconds. And the model must be also sophisticated enough, must be up to the task. And of course, you have to not break the machine at the meanwhile. So we want to use recurrent neural networks because they operate on the time domain. So here I'm showing you the success story of the LSTM. This is the long short-term memory model, which is more widely used as the Gated Recurrent Unit. And these kind of models are being used to predict time series. They are being used to do generative AI, so for instance, translation. They have been using the reinforcement learning to beat humans at every game they touch. And they also have been proposed as controllers for nuclear fusion. Here at CERN, they have been proposed for particle track reconstruction. They can do anomaly detection for triggering and also classify, jet tagging. So what is the Gated Recurrent Unit and how does it work? On the right side, you can see how recurrent neural networks operate in time. So at time 0, you get a bunch of numbers, a vector, and the model spits out another vector, the hidden state, as it's called. This is both the output of the model, but it's also used as input for the next time step, in which we can think of this hidden state as a compression, a distillation of all the observations that you had before. And this works somehow like a memory. If you zoom in inside the model, it looks like this. But the important thing, what I want to illustrate here, is that we can see which kind of numerical operations we need to implement in hardware. So at the left side, these are called gates, the Z, R, H hat, and the new hidden state gate. And we can see that the bread and butter of our machine learning is the matrix vector multiplication. Then you have a bunch of the results of these matrix vector multiplications are vectors in which you add them together, and then you apply activation functions. In the, you also have to do some element-wise multiplications. As I said, additions, subtractions, these are trivial to implement. The model also has some computational dependencies in the sense that in order to, as I said before, in order to compute the next stuff, you need to have the previous hidden state. If you don't have that, you cannot go on with the computation. Also, within the same time step, you have to first compute some gates in order to use them later, such as the R and the Z gate and the H hat gate. They have to be computed before the new hidden state. So the promise is that we can somehow accelerate all this computation by using our hardware, which is the AI engine of the Versal. And what is the AI engine? Is a tiled array. It's an array containing AI engine tiles, 400 of those, which each one has its own memory and its own processor. It can be a scalar processor or a vectorized processor. All these communicate with each other, and we'll see exactly how. For all our purposes, the AI engine can be thought as sitting right next to the FPGA fabric of the Versal, and it communicates with it via interface tiles. And this is the main throughput bottleneck of our system. Inside an AI engine tile, a very simplified version is if you want to use the vectorized processor, you load 2 registers, either from your local memory, or you can directly stream into the register. And then when you are ready, the computational unit will consume the data, will do a bunch of computations, and will store the result in the accumulator register. How do all these things communicate with each other? Well, we have 4 possible connectivity. The middle tile can read and write to the nearby memory banks of the nearby tiles. It can either consume data or write to them. And this is a local connectivity. If we want to send data from a tile to any other tile, we basically use the classic XI4 stream, interconnects, and we go through switches. We basically somehow DMA to another tile, which go through the switches, then a small buffer, and then we either stream directly into the vectorized processor, the registers, or we write into memory. These also have the powerful feature that we can broadcast, we can copy the same signal. Each tile can have 2 stream inputs and 2 streams outputs. We also can flash the accumulator register directly into a neighbor. This is the most local connectivity that we can have. And the most interesting one is the one that allows us to do networking inside the AI engine. So by using a header system, you can distribute data packages or aggregate from one tile to multiple or from multiple tiles to one tile. And you can also have an interplay via the programmable logic. So the programmable logic can prepare headers and directly send to one AI engine tile. So how do you program all this? You start by writing C++ functions, which are called kernels. And here, this example tries to showcase the fact that you are using 4 AI engine tiles, and you have instantiated in the first 2 the same kernel that you wrote. So the first kernel will do some multiply accumulate operation. Then the results are being sent to another AI engine tile, which adds the results. And then this result gets sent to another AI engine tile, which implements a lookup table. A random example, but not so random, as you will see. Once we have written our computational pipeline, we can encapsulate this whole computation into an abstraction, a computational graph. And this is very useful because now you can use the same computational graph to instantiate it many times into a top graph, which uses subgraphs that do some kind of computation. A very important also feature of the AI engine is that we can pass parameters without specifying exactly some stream connectivity or something. We can just say that they are runtime parameters, and there is a construct inside that allows us to pass parameters from the PS directly into an AI engine tile and write to its memory. And this will be very useful because in the matrix vector multiplication, the matrices, you only need to write the matrices once. So now I'm going to explain to you how we do this, and all numerical computations are done in floating point single precision. But we have to use native data types that work only on the AI engine, and those are vectors of 4 floating point numbers. And this also means that our matrices are quantized to that size, but that's fine. So let's pick one of the gates of the recurrent neural network. We want to distribute as much as possible. We have all this computational power of 400 AI engine tiles. We want to distribute the matrix vector multiplication. If we do so, then we can tackle all these matrix vector multiplications, even the one that is not squared, because it's a little bit with a twist. So a bit of linear algebra. There are two ways. Actually, there are more ways than that, but I'm showing you two. There is one way to do it is that you dot product one row of the matrix with the vector, and you get the first element of the result, or an element of the result. The other way to do it is that you can multiply a column of the matrix with the first element, then the second column of the matrix with the second element, add to the previous result, and then you go on until you consume all the columns. Remember, inside the AI engine tile, all we can do is the multiply accumulate operation. So we're going to load some partial rows of the matrices onto a tile. We will consume from that the vector register, and then we're going to stream the vectors that are being observations or the hidden state directly to another vector register, and we're going to do the multiply accumulate operation. So how we do this? Well, let's say we want to create a subgraph that does exactly this computation. Once we do, we can instantiate it many times and just distribute to the whole AI engine. We're going to do the first four floating point numbers of the matrix with the first four floating point numbers of the vector, element-wise multiplication, and store the result. Then the next four floating point numbers, element-wise multiplication, and add to the previous result. If you consume the whole row, then you have done, you are left with a vector of 4 numbers. You need to reduce it, just add its number individual, and apply an activation function. Then you have the first element of your computation. Now, let's say you distribute this computation to another set of kernels that can do this concurrently at the same time. They do not communicate with each other. Once you have done this, you need to aggregate the partial results. And basically, this is done with the packet stream, this connectivity thing that I told you about. And we are a bit limited to that. We can use up to 32. And with a small trick, you can make double that. So this is how it actually looks like on the Vitis software. So the matrices are being stored as runtime parameters into the local memories. This kernel will do some row of the matrix with the input vector, with dot product. The same does this kernel, and then this kernel will collect the results of the previous kernels, reduce everything, add everything together, and apply the sigmoid activation function. Then you have the construct of the merge, which you are merging 16 of those in this example, and you're also using a kernel that does so. So this same recipe, this same subgraph will be instantiated for all these gates. And the last gate is trivial because it doesn't have any parameters of the model. Then the next, there is a second template, which I'm not going to talk a lot, is that you do this kind of operation. So you use the same MAC of 4 numbers, but now it's a little bit transposed, let's say. The twist is that now you can apply the activation function 4 times concurrently. And it only changes a little bit on the implementation, which you do the WX, UH. Then you have a kernel that adds everything and just splits to apply the sigmoid into 4 different kernels. Then the merge construct is exactly the same as before. So how do you now apply these activation functions? Well, the base solution, lookup tables. You do lookup tables. This is the go-to solution for when you are applying these machine learning models to FPGA. And it can be very, very fast. But on the AI engines, you are limited in memory. And you also need this kind of memory for heap and stack purposes. And you also need to rescale from a float to index range and then to integer. And in the end, this takes around 70 nanoseconds to implement. There is also the consideration that you do everything in floating points, and now you have to quantize the activation functions. I mean, does it really worth it to do everything in floating points? But there's also the cool solution. And the cool solution is to scratch the original sigmoid and tanh and actually train the model with splines. So you don't really need to use the true sigmoid and the tanh. You can create these third-order splines, or you can up the order as much as you like. And then now you can actually compute the splines very, very easily, because once you have these partial results of the inside the gate, now you have a number. You just calculate some orders of the powers of this number, and you have a constant vector that carries the constants of the polynomial. You multiply and you reduce. And this actually is faster than doing a lookup table. And even if you don't use the vectorized processor just for one number, it's even faster than that. It's at 45 nanoseconds. So these are the latencies only using the raw implementation, the first one. So we start with a couple hundreds of nanoseconds for a forward pass of the model. And we reach around 1.4 microseconds. Now, FPGAs can be faster than that, but do they scale the same? And here we can see that you can have some very, very large input vectors with a very, very realistic hidden state of 64, in which you are using almost 3/4 of the AI engine, and you can actually have some very, very good timing results. So one problem is that the dimensions of the matrices are not generally not the same. So what you want to do is change the design onto doing the same MAC operations in all kernels, and we are working on this. I propose some solution, but I think we're going to skip that. Now, I want also to say that all the kernels, all the AI engines in Tile, the AI engines are free-running kernels, which means that they operate inside an infinite loop, and they just stall when they wait to accept data or they wait to pass data. The compiler had a problem with that, but there are some scheduling pragmas you can use. I'm going to skip that. Also, the compiler uses a placer to physically place the AI engine tiles. You can also do it by hand, and it could be beneficial in the merge constructs because there is actual physical data congestion on the same physical lines. Now, outside the hardware, you need to correctly reshape the parameters of the model so you can pass them at the correct shape to be macked. And you also need to design your own activation functions. So in the future, we want to propose a hybrid solution. So how can we use both the AI engine and the FPGA fabric? Well, just enter the AI engine and do only the matrix vector multiplications. Then you can go out of the AI engine and spare it from merging and doing all this data aggregation, and actually implement lookup tables on the FPGA fabric. And this should be much, much faster. Then you enter again, you do the next set of computations, and then you can go out again to implement the next set of activation functions, and then you enter again to calculate the new hidden state. This interplay between FPGA and AI engine is completely doable. It doesn't cost anything in latency, and it has the possibility to be extremely fast. So in the future, we also, if we crack the GRU, and we are very close, we can easily do an LSTM, which is basically 2 more gates. Or we can do cutting-edge modules like the XLSTM and the RWKV. And I'm going to close with a final remark that this started as a work to do reinforcement learning. So in that framework, you only have to do just one forward pass on the model. And the model, once it operates in a reinforcement learning framework, is machine agnostic. It doesn't really know which machine is controlling. It just minimizes a loss function. So once you can do microsecond inference using the AI engine, then you could use these frameworks for other machines, let's say quantum computers or other stuff, or nuclear fusion. So thanks a lot. I hope you enjoyed it. And you can also find the code for the GRU in this GitHub here. Thanks a lot.
Thank you. Questions?
Yeah, hi, thanks for the interesting presentation. I have two questions. One question would be, how many AI engines did you utilizing?
So it depends how much you're distributing the computation. We also allow for a reuse factor, if you're familiar with SLS4ML. So you can compute more than one rows, for instance, in a subgraph, right? So it depends on how many rows you have, basically. So it depends on the hidden state. We can go up to 294, if I remember correctly. I have, on the latencies, I've put also the resources. Yeah. And you can see how, so the resources are AI engine tiles that we are using.
Okay. Yeah, thank you. And the other question would be, so this is a really nice way to implement the matrix multiplication and distribute it over multiple AI engines. Would it make sense, based on your experience, to make one AI engine do all the computations that you need, but then you tile the big matrix into 400 different tiles?
Sorry, I didn't understand, because you said one AI engine tile to do all the computation?
Yes, so you don't have to move data between AI engines, because you can just have it locally, and then you can then distribute the tiles over all the 400.
I see. The problem is memory. You have only 32 kilobytes of allowed memory. And the first implementation was actually done like this, the most compact way possible to not pass data around. And if you do so, you're actually limited by memory. So how much you can scale up the model, you cannot actually store the parameters inside. So this kind of implementation also allows you to scale up the model to very, very big, to a lot of parameters. So you can touch up to 10 megabytes of parameters.
OK, thanks.
Thank you.
You said that the type is floating point 32. As far as I understand, very many models work with smaller data types exactly to migrate this problem with the memory. Is this the only data type that is available at the moment?
No, absolutely not. It's just the most precise data type. And it depends on the application of these models. Sometimes going up to the 5th decimal place actually carries some information. And sometimes it absolutely doesn't. But on the AI engine, you have the possibility to use integers and floating points, and also complex floats, if you want. So we could do fixed point arithmetic by using integers, and then you change the decimal place on the accumulator register. So you could be fast. And even the pipeline of computation is faster with integers, of course. But we chose the worst-case scenario for this implementation. You can always template the data type and change data types. In the new AI engines that AMD gives you, the ML types, it also gives you the B floats, which are floats with 16 bits.
OK. If there are no... one last question.
Very nice work. I was wondering about the future works. You mentioned about offloading of some activations or other types of high granularity operations to the fabric of the FPGA. But in that case, to the best of my knowledge, there is no directly IP interface or other things you can directly connect AI engine.
Sorry, I cannot hear you.
Okay. Can you speak closer to the microphone?
OK, sorry. So to the best of To the best of my knowledge, you cannot directly access the AI engine as a programmed IP core, basically. And in that case, how would you offload the data from the AI engine to the fabric? And because if you go through the CPU, there will be a high latency, and how is that solved?
I cannot hear the question very well. So you say that there is a problem offloading from AI engine to the FPGA fabric.
Yeah, how do you handle the communication there? If it goes through the CPU, then it can be very slow, and the latency is very high.
Yes, so the communication is done by using interface tiles that are exactly, they only do this job. There is also one, you can also connect. So the Versal has something called the network on chip underneath, and you can go, so the AI engine can either communicate with DDR memory directly. You can DMA from memory directly to the AI engine tiles, or you can use DMAs in the FPGA side, on the programmable logic. Yeah. If you do through the programmable logic, then you're using these interface tiles, and you are limited there. You have some throughput problems. So, but you're not using CPUs. It's DMA. It's always DMA, even from DDR memory.
Okay, thanks.
Okay, let's thank Michail again. Yeah.